A vehicle's fuel consumption is important because it makes up a significant part of its running costs. But in recent times, it has assumed even greater significance. Because it involves the consumption of a fossil fuel, namely petroleum, and the emission of CO2 into the atmosphere, it has come to the attention of the public and politicians, and has become the subject of legal restrictions and rules. To discuss how fuel consumption might be reduced, we need to understand how things interrelate. Fuel consumption is determined by the design of the vehicle, its drive system, and the operation of auxiliary consumers. It is also considerably influenced by the driving style of the driver. These points will be discussed in the chapters that follow. A vehicle's fuel consumption is very much dependent on how the vehicle itself is used. In order to obtain comparable figures, many countries stipulate standardized test cycles for calculating fuel consumption. In the European Union, as well as some other countries, the test cycle for passenger cars and vans is the New European Drive Cycle. This includes an engine cold start, 4 urban cycles, and 1 extra-urban cycle. By contrast, truck and bus engines are assessed in accordance with the European Stationary Cycle, in 10 different load states and at idle. In addition, there is the European Transient Cycle, which measures fuel consumption for 3 simulated trips, 1 urban, 1 extra-urban, and 1 on the motorway. Depending on the use of the vehicle and the equipment fitted, the actual fuel consumption may differ from the standard figures. Fuel consumption and CO2 emissions are closely related. The frequently debated limit of 120 grams of CO2 per kilometre corresponds to the following fuel consumption figures: 5.2 litres of petrol per 100 kilometres, 4.5 litres of diesel per 100 kilometres, or 4.4 kilograms of natural gas per 100 kilometres. The different fuel consumption figures arise because of the different chemical compositions of the fuels. Select the fuel type and fuel consumption, and the CO2 emissions will be calculated for you. A vehicle doesn't just consume energy whilst it is in operation. Energy is consumed throughout the entire life cycle of a vehicle, in other words, when its materials are manufactured, when the vehicle is built, during the extraction and refining processes for the fuel, as well as the transportation of it to the service station, and finally, when the vehicle is disposed of. However, energy consumption during use remains the most significant part, which is why this CBT will look solely at this particular aspect. Daimler's work is primarily focused on developing fuel-efficient designs for both vehicles and their drive systems, as well as on optimizing the use of auxiliary consumers. Daimler cannot and has no desire to tell the driver what to do, but will provide the necessary tools to make it easier to adopt a fuel-efficient driving style. There is a limit as to how far you can go to reduce fuel consumption, and that limit is reached when it becomes no longer possible to use the vehicle under the intended conditions. This relates to issues such as transport volume, payload, safety, and the level of comfort demanded by the customer. In which part of the life cycle is most energy consumed? Click on the correct answer, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. The largest amount of energy is consumed during vehicle operation. When a vehicle is moving, it encounters various driving resistances. Air resistance, rolling resistance, climbing resistance, and acceleration resistance, in other words, mass inertia. The greater these resistances are, the higher the fuel consumption. Take a look and discover what specifically influences each driving resistance. You've seen how the resistances interrelate. Now let's have a look at each type of resistance individually. Air resistance is obtained by multiplying the frontal area A by the CD value. This latter figure indicates how much more aerodynamically efficient a vehicle body is when compared with a box with a vertical front face. Air resistance increases with air density ρ and with the square of the driving speed. In other words, when the speed doubles, air resistance quadruples. Consequently, it plays a particularly important role at high speeds. If you wish to see some examples of frontal areas and CD values, please click on the button marked More Info. Rolling resistance depends on the tyre design, its air pressure, and the weight of the vehicle. At high speeds, the coefficient of rolling resistance, F, increases because of the faster flexing action. On passenger cars, tyres known as low rolling resistance tyres can be used to reduce fuel consumption. On vans, trucks and buses, wheels called super single wheels have come into use recently instead of twin wheels. There is less flexing here because it only occurs in 4 rather than 8 tyre sidewalls. Climbing resistance depends on the mass of the vehicle and on the angle of slope. Generally, an uphill drive is normally followed by a corresponding downhill one, when the potential energy gained previously is released again. The downslope force overcomes the other driving resistances either partially or fully. If the downslope force prevails, then, in a conventionally driven vehicle, the released energy is converted into heat in the brakes. A hybrid vehicle, however, is able to store this energy for later use. Acceleration resistance depends on the vehicle mass, because the mass inertia opposes the acceleration. When accelerating, however, the vehicle gains kinetic energy. It is released again when the vehicle slows down. Because the vehicle must be braked, this energy is usually converted into heat in the brakes. Hybrid drives can store this energy instead. You have seen that the weight of the vehicle is a factor in rolling resistance, climbing resistance, and acceleration resistance. Reducing vehicle weight is therefore particularly important when reducing fuel consumption. The weight of a vehicle can be reduced first and foremost by lightweight construction. This involves the use of light metals such as aluminium or magnesium, and plastics. Special high-strength steels offering the same level of strength with less material are another lightweight construction method. Move the mouse over the diagram to learn more about the materials used in a modern vehicle body. Where commercial vehicles are concerned, the vehicle's required payload imposes certain limitations. A high payload requires an appropriately solid and consequently heavy vehicle structure. In the case of passenger cars, it is primarily crash safety, but also the customer's expectations of comfort that set the limits where weight reduction is concerned. At higher speeds, air resistance has a considerable influence on fuel consumption. It can be reduced by having a small frontal area and by creating a good airflow around the smooth vehicle body, under the vehicle, and through the cooling system openings. However, though a solar car like this one scores top marks where air resistance is concerned, it's hardly practical for everyday use. On commercial vehicles in particular, it's important to maximize the load compartment volume for the legally stipulated overall vehicle length. As a result, a relatively steeply raked, in other words, aerodynamically inefficient driver's cab is required. In addition, by necessity, many commercial vehicle bodies do not feature smooth contours. In the case of passenger cars, air resistance has been substantially improved by measures implemented on the vehicle front end. Smooth trim. Shallow raked windscreen. Smallest possible air intakes. Nevertheless, it's still possible for a vehicle to have a distinctive face, like the E-Class here, which has a CD of 0.25. Ideally, the rear should be shallow sloping, though this is not really possible on estate vehicles. Even on saloons, you have to maintain enough headroom for the rear passengers and ensure that the design of the vehicle body facilitates clear vision. The underfloor should be panelled so that it is as smooth as possible. However, the exhaust system still needs to be cooled. What driving resistances does vehicle weight influence? Click on the correct driving resistances, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. The weight of the vehicle influences all driving resistances except air resistance. Which design aspects influence air resistance? Click on the correct influential factors, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. Air resistance is influenced by many factors, but not by the weight of the vehicle. The driving resistances dictate how much torque needs to be delivered to the wheels so that the vehicle can maintain the desired speed. How much combustion energy needs to be obtained from the fuel for this purpose? Consider also the losses in the drivetrain as a whole. Auxiliary consumers need to be powered to generate electrical energy in the alternator and pressure in the pressure reservoirs of trucks and buses. Some are also driven directly via the belt drive, for example, the refrigerant compressor or power steering pump. The power consumed by these components is playing an increasingly significant role. Internal engine friction, for example, bearing and cylinder lining friction, needs to be overcome, as does friction in the transmission and final drive. Gas cycle losses occur when fresh air is drawn in through the air filter, throttle valve, intake manifold, and intake valves. This uses up power that has to be provided by the motion of the pistons. A similar phenomenon occurs when the exhaust gases are discharged through the exhaust system. The greatest losses, however, relate to thermodynamic efficiency. A fundamental principle of physics states that in combustion engines, only a proportion of the combustion energy can be converted into motion. Waste heat that has been transferred to the coolant can at least be used to heat up the passenger compartment. However, a lot of the heat escapes unused with the exhaust gases. Discover more about the losses in petrol and diesel engines at full load, part load, and idle. At idle, of course, no power is delivered to the wheels. The fuel consumed while stationary is simply fuel lost. This demonstrates how important an automatic start-stop system is. The diesel engine is more thermodynamically efficient than the petrol engine. This is due to the greater difference between the lowest and highest combustion chamber temperature. At full load, most of the combustion energy is delivered to the wheels. This will be discussed later when we look at fuel-saving tips for the driver. By the way, the thermodynamic efficiency principle does not apply to fuel cells, batteries, and electric motors, which is why such drives are much better able to utilize the energy supplied. Therefore, and in order to achieve zero tailpipe emissions, the car of the future will be driven by electric propulsion. But let's stay with current technology. Diesel engines have reached a high state of development, thanks in particular to the introduction of high-pressure direct injection, the common rail system for passenger cars and vans, and the pump-line nozzle system on heavy commercial vehicles. Implementing even higher injection pressures and controlling the injection process by means of multiple injection will bring further improvements. Making the mixture even leaner would improve fuel consumption, but would worsen emissions. A further reduction in fuel consumption via this route is only possible by utilizing a sophisticated exhaust gas aftertreatment process involving the use of urea, a process known as Blue Tech. There are possibilities for improving petrol engines. Losses in the inlet port can be avoided by injecting the fuel directly into the combustion chamber. In low-load conditions, the engine can be operated in lean burn mode with an inhomogeneous mixture. Fuel consumption is reduced, but emissions worsen. And, as on the diesel engine, a more complex emission control process is required as a result. Select the different modes to observe the injection timing and mixture formation. A new type of petrol engine is currently in development. In part-load conditions, it works like a diesel engine with auto-ignition. This new engine goes by the name Diesauto. The engine switches to conventional spark ignition by means of spark plugs when its running characteristics need to be kept stable, in other words, during idling and at full load. In spark ignition, the mixture is ignited by the ignition spark. The flame then propagates out. Consequently, combustion is non-uniform, and the entire mixture is not always burned. By contrast, autoignition occurs when the mixture reaches ignition temperature as a result of being compressed. It occurs simultaneously throughout the entire combustion chamber. As a result, combustion is uniform and complete, bringing considerable fuel savings. Switching between the two modes not only requires the form of ignition to change, but engine compression as well, which means the valve opening times have to be adjustable. A large displacement engine has a good deal of internal friction and is also heavy. By using forced induction, for example by means of a turbocharger, it is possible to achieve the desired engine power output with a smaller displacement engine. This will have fewer friction losses. The lighter engine will also reduce vehicle weight, and you've already learned in Chapter 1 what this means. In situations where the engine does not have to deliver any drive power, the consumption of fuel can be avoided. In overrun situations, such as when coasting or when driving downhill, the fuel injection process is suppressed. This is known as overrun cutoff. When the vehicle is stationary, which can be detected from the vehicle's behavior and the actions of the driver, the engine is switched off. It is automatically restarted when the vehicle continues on its journey. This is known as the Eco Start-Stop function. This requires a special starter system with a belt-driven starter alternator or a special pinion starter. Hybrid drives have a combination of at least two drive systems, usually an electric motor and a combustion engine. The torque characteristics of the electric motor and combustion engine complement each other. In situations where the combustion engine operates inefficiently, such as at low loads or low engine speeds, the electric motor is able to provide some or all of the drive power. When full load is called for example when overtaking, both the engine and motor come into operation, combining their torque outputs. This way, the desired performance characteristics can be achieved with a small fuel-efficient internal combustion engine. All hybrid versions feature the Eco Start-Stop function, since the electric motor also serves as a powerful starter. However, it is in the recuperation process where most of the savings are made in a hybrid drive. In overrun situations, kinetic energy is released. But instead of this manifesting as heat in the brakes, the electric motor works as an alternator to convert it into electrical energy, which is stored in a special drive battery. This electrical energy can then be usefully deployed later on, for example in boost mode, when driving the vehicle using electrical propulsion, when starting the vehicle, or for supplying the onboard electrical system. In manual transmissions, the highest or most used gear is frequently designed as a direct gear. As power is not transmitted via gear wheel pairs, friction losses are lower. In addition, the highest gear is designed as a low revving gear. This is also referred to as a long ratio gear, and particularly if the ratio is greater than 1, overdrive. This means that in the highest gear, the torque falls below the level of driving resistance before top speed is reached. However, top speed is usually achieved in the second highest gear. Consequently, when driving in top gear, as is typically the case on long-distance journeys, the engine runs at lower engine speeds and uses less fuel. Automatic transmissions have a torque converter. When power is being transferred, the converter incurs flow losses, which is manifested in the heating up of the transmission fluid. Consequently, as soon as the operation of the automatic transmission permits it, the power flow is directed through the converter lock-up clutch, which is virtually loss-free. You can switch between the two power transmission methods for comparison. Passenger car automatic transmissions or automated manual transmissions may have sporty or comfort-orientated gearshift modes. A comfort-orientated mode shifts to a higher gear earlier and shifts down later. The result is lower engine speeds and better fuel consumption. When the vehicle is brought to a stop and the brakes applied, the 7-speed transmission automatically interrupts the flow of power to reduce losses while the vehicle is stationary. This function is known as Power Cutoff D. The automated manual transmissions on trucks can also have power or economy-orientated gearshift modes. An economy-orientated gearshift shifts up earlier and shifts down later, resulting in correspondingly lower engine speeds and better fuel consumption. The eco-roll function of a truck transmission disconnects the powertrain during the journey if neither drive torque nor braking torque are required, for example when coasting. This reduces fuel consumption even further. Can you remember what is responsible for most losses in a drive system? Click on the correct answer, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. Heat loss from the combustion engine is responsible for most losses in a drive system. Why is a hybrid drive advantageous in terms of fuel economy? Click on the correct reasons, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. The hybrid drive has many advantages, but it does not make the vehicle lighter. The auxiliary consumers obtain the power required to operate them from the combustion engine and are therefore responsible for a proportion of the vehicle's fuel consumption. A distinction should be made here between mechanically driven auxiliary consumers, electrical auxiliary consumers, and pneumatic auxiliary consumers, the latter being predominantly found on trucks and buses. Electrical auxiliary consumers are supplied from the on-board electrical system battery. Switch on the light. The draw of current causes the battery voltage to drop. The charge control system detects this and actuates the alternator. This then charges the battery and compensates for the current drawn off. Consequently, the load on the engine is not a constant one, but rather merely equal to the amount of power being drawn off. This is the principle of on-demand control. It's a similar matter with pneumatic auxiliary consumers. The compressed air drawn from the pressure reservoir is compensated for by a corresponding charge from the engine-driven air compressor. This is also on-demand control. In the past, mechanically driven auxiliary consumers were driven continually and consequently consumed energy even when they were not required. However, they can also be operated on demand, as this state-of-the-art engine demonstrates. To see examples, find the coolant pump, the refrigerant compressor, and the power steering pump. On the volume-controlled refrigerant compressor, the stroke of the plunger can be adjusted steplessly, enabling the drive torque to be adapted to cooling requirements. The coolant pump is fitted with a thermostatic valve, which enables the coolant to circulate in a small coolant circuit when cooling demand is low. This not only permits engine operating temperature to be achieved more quickly, but also reduces pump motor power output. On the Eco power steering pump, a bypass valve is controlled electronically as a function of steer angle, driving speed, and other variables. When it is closed, pressure for the steering assistance is generated. If steering assistance is not required, it is opened and the pump does not generate any pressure. Drive torque and consequently fuel consumption are reduced as a result. Some auxiliary consumers, such as the radiator fan or fuel pump, have also been switched to regulated electric motor drive in order to save fuel. The alternator places a considerable load on the combustion engine. Usually, the alternator is actuated according to the demand for electrical power, for example, after the engine has been started and once the reference voltage has been reached. This is done by regulating the voltage as you have seen before. As part of the energy management function of the onboard electrical system, extra power is also generated when excess kinetic energy is accrued. In overrun conditions, in other words, when decelerating or driving downhill, the alternator voltage is raised. By contrast, in conditions of load, the excitation voltage is reduced or even switched off completely to relieve the strain on the engine. Charging is otherwise temperature controlled to protect the battery. However, there are limits to the fuel-saving measures that can be implemented on auxiliary consumers. For example, if as a result of the measures, the vehicle's operating reliability could no longer be guaranteed. We're referring here, for example, to the oil and coolant circuits. Driving safety must not be compromised either. Here we're thinking of the lighting, window heating, power steering assistance, and brake servo assistance. The level of comfort demanded by the occupants, such as electrical adjustment, climate control, and telematics systems, must also be provided. Where the electrical power supply is concerned, the ability to start the vehicle always takes priority. Which statements describe on-demand control? Click on the correct statements, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. It's possible to implement on-demand control for all auxiliary consumers. It reduces fuel consumption because power is only drawn from the engine when the relevant auxiliary consumer is operated. When does an alternator on a vehicle with alternator management charge the starter battery more? Click on the correct statements, then That's incorrect. Try again. That's also incorrect. The alternator charges the battery more when a large amount of power has been drawn off and when kinetic energy is available. The driver has a huge influence on a vehicle's fuel consumption. This example will convince you of this fact. Drive the vehicle to its destination. First, try to adopt as swift a driving style as possible. Here's your fuel consumption for this journey. Now drive the vehicle to its destination again. This time, pay attention to the phased traffic lights. Here's the current fuel consumption. Compare the two journeys. A fuel-efficient driving style involves upshifting as soon as possible when accelerating, driving in the highest possible gear, in other words, at the lowest possible engine speeds and high torque, and adopt an anticipatory driving behavior, in other words, avoid unnecessary acceleration and braking. The fuel consumption advantage at low engine speeds and high torque can be explained by the specific fuel consumption of combustion engines. The diagram shows the maximum torque curve as a function of engine speed, the full load performance map in other words. Any point below it can also be achieved in the part load range. The blue line shows all the operating points that produce a very specific engine power output. This can be achieved in different ways. With high engine speed and low torque, or with low engine speed and high torque. Take a look now at the fuel consumption. Select the point on the power curve where you think the lowest fuel consumption will be achieved. It's more economical than that. The lowest fuel consumption for the desired power output is achieved with low engine speeds and high torque. On passenger cars with a manual transmission, gear shift recommendations and fuel consumption figures can be displayed. In trucks, the engine speed ranges are also color-coded to assist the driver. The optimum speed range is marked in green. The yellow range should only be used in specific situations, such as when accelerating and overtaking. The least favorable range is marked in orange. whilst there is a risk of damaging the engine in the red range. When operating a vehicle, consider the indirect fuel consumption of the auxiliary consumers. Seat heating, window heating, and demisting require a power of more than 1 kilowatt. You should switch these off, therefore, as soon as driving safety and comfort permit. The daytime driving lights, of course, also consume electrical power. But at around 15 watts, the safety gained by using them is to be considered greater than the energy they consume. When using the vehicle, consider the driving resistances. Click on them to find out how the resistances may be reduced. Only use the roof or rear-mounted racks when you have to transport something. They have a detrimental effect on the vehicle's CD value. Ensure that the tyres are inflated to the correct pressures. If the pressure is too low, rolling resistance is increased, more fuel is used, and the tyres are prematurely worn. Avoid carrying any unnecessary weight in the vehicle. Each additional kilogram increases climbing and acceleration resistance, as well as rolling resistance. Clear out the boot. There's really no point in having the snow chains in there during the summer. You have seen many ways in which a vehicle's fuel consumption can be reduced. Most of these aspects are implemented in Daimler's vehicles. For example, with the Blue efficiency models in the passenger car sector, and the BlueTech Eco initiative and Clean Drive technologies for commercial vehicles. Some ideas could be even more far-reaching, as demonstrated by the Blue Zero concepts. At present, however, these are not yet viable for the customer on account of purchase costs or infrastructure problems. Consider also that whilst saving fuel is important, you shouldn't deny yourself the occasional bit of driving pleasure and comfort. At which operating point is the fuel consumption of a combustion engine at its lowest for a given power output? Click on the correct operating point, then confirm by clicking on OK. That's incorrect. Try again. That's also incorrect. Fuel consumption is at its lowest at low speeds and high torque.